So here I talked to you before using this relationship. It comes down to the fact that efficiency is what you put it in, how much you get out, and that becomes essentially 1 plus QC, QH, 1 minus TC, TH. Okay? And this portion is actually something that is using the fact that the reversible heat divided by temperature is defined by entropy change, and entropy being the state function, we can calculate that. But real situation is when A to B, and this is an isothermal, I'll just using more simply isothermal, and B to C, adiabatic, all reversible, and C to D, isothermal, D to A, going back to this, and then adiabatic reversible. So this is a one. And do you know, we know how much of the Q and how much of the work do we get. And we are actually more interested in the work itself. Okay? But we know this already. You guys remember this? You can do it. You can be a, I don't know, Mason cycle, right? If you finish this table. I mean, let me just do this delta U. So this one is delta U 0, right? And this is a work expansion, the ideal, so work reversible minus nRTH natural log VB VA. I can do that. And let me just call this as a 1, 2, 3, 4. So that is our first one. Okay, I can do. What's my second one? This Q is, which is we call QH, right? QH is essentially nothing but minus QW1, which is the reverse of that. So I can do that. But this is a actual equation that was used in the thesis by this Carnot. And what's my here? B to C adiabatic. Oh, it's a 0. I'm happy. And then you guys know that this is a CV delta T. So that will be a CV. Temperature is changed from high temperature to low temperature. So there was a T high, now down to T cold. So for your final temperature, I mean CV, T final, which is cold temperature, pH, initial temperature. Okay, so that's my delta T. What about this? Okay, this is, I think we defined the QC, and that's my W. I guess this is my W2. This is a W3. Same deal here. NR, now the TC, natural log. The final volume is D, initial volume is C. So that's what you do. And your delta U is 0. Okay? That's your delta U. And your final one, because adiabatic, 0. And then I guess we can calculate CV delta T. This time, CV, this is a work 4. CV, your final temperature is high temperature from cold temperature. Okay? Remember this? This is a pH. This is a QE0. This is a TC. This is QE0. So A, B, C, D. So when you do that, this change, your temperature is from cold temperature final, from initial temperature high. There's this process of adiabatic compression. Your final temperature is TH, your initial temperature is TC. So you do that. And then what I call work over cycle, okay, which is, as I was mentioning that, and this is gone, right? To compensate, and this is the only thing left, which is minus nR pH natural log volume ratio. And this one minus nR TC natural log VDC. So this is a very elaborate way for me to do. Okay. So what's my work over Q over cycle? QH QC, right? And then delta U over cycle, which is the Q cycle, work cycle, and then this is a QH QC plus, you got exact relationship shown up here. Okay? And then I'll just keep it work cycle as here, because it's 0. Okay? So the one tricky part is this. The volume here to there, and volume compression factor from here to there. This is an expansion, this is a compression, right? In a way, this volume has to be chosen when things are happening adiabatically. They have to close the gap. And that volumetric ratio is actually can be canceled out, and it can be shown up. Okay. Okay. So far so good, and then let's go back to my original interest. So I can do that in my thesis, and then I'll go back to C. All I want is changing this onto something that is temperature variable, right? If you look at that, you see that QH is defined, the inverse sign of that. QC is defined by inverse sign of that. You see that? Yeah. So what I do is now, okay, from this relationship, QH, I'm interested in QC, QH, which is, I guess, minus work number 1 minus work number 3 is nRTH volumetric ratio of BA, nRTC ratio of BC, BD over BC. Okay. D over C and B over C. Yeah. So this volumetric ratio are essentially inverse. In a better term, actually, this ratio VV, VA, this ratio and this VC over VD, they are same. I can prove that they have proven in the textbook using the adiabatic relationship and how flipping the equations around. So what it does is I can switch this one now because it's essentially inverse relationship, and I can say that's essentially C and the D with the negative sign going up, right? And then we are in a good business. I love to get rid of this, and this is gone now. Okay? So finally, what you got? QC, what? I'm sorry, QH, Q. What did I did something wrong. Let's just say QH over QC. Okay? I was trying to use this one, but let's just say QH over QC is this relationship. That's true. Okay? So the QH, QC, according to this, minus PH, PC. This is another way, new perspective on using this. What I just said is temperature ratio, heat ratio goes in and out is a temperature ratio in the isothermal reversible expansion process. Can I use that? Right? Heat ratio, temperature ratio with a negative sign. So this one can be derived this way. And he completed it. And what the Roth Kelvin did is he flipped the story upside down. It looks like this whole process, this is exactly what he did. It looks like the whole process, if I define Q reversible divided by T as a new function, right? And this is really creative, new function, and I can derive this, and that's supposed to be 0. And I got this relationship here. So therefore, it must be this guy, Q reversible by T must be essentially one change in one of the state function, and let's call it as an entropy. And that's what happened. And we don't have to live through the history. Okay, I mean I have to teach you guys what has happened, but you just cut this short. Cut it short. Cut this out. Cut this out. Right? All that matters is here is essentially this relationship can be derived by the way that you don't like, right? This is the way that you don't like, or this is the way you would like, right? This is the way you would like, and we just got this relationship. And so this can be done using this diagram, and then I can finally get this equation. So this equation is actually practically, like I said, used in the industry people who's developing jet engine, because they don't have it's a very complicated engine that is actually happening in the inside of the diesel engine. In the internal combustion engine is a little bit more difficult. So they are having a Otto cycle, there is a diesel cycle, they have a different cycle showing the different ways of how things are going in and out. But eventually it comes down to the fact that this is what you can have is how much of a heated gas, exhaust gas, and this is a ratio. And this is how the maximum efficiency that engine can have, and we will have a lower efficiency than. All right, it's a long class. Thank you.
Would you say about